We have with us Maaike Zwart from the University of Oxford, who will be talking to us about distributive laws in the Bohm hierarchy. So before we begin the talk, a couple of usual announcements. So first thing, this talk is getting recorded. And as always, we encourage everybody to keep their video on as much as possible to get a semblance of a real physical talk. The slides are already uploaded on the OWL's page. So if you prefer, you can download them and look at them as the talk is proceeding. If you have a question to ask, you can use the raise hand feature, and I will pay attention to the whoever is raising their hand. Otherwise, I guess we are good to go. So I'll hand it over to Maaike. Maaike, it's all yours. The floor is yours.
Thank you very much, and thank you very much for inviting me to speak here today. So I've just finished my PhD thesis, and it's all about distributive laws and for monad compositions, but even more importantly about when those distributive laws don't exist. So we'll have a little look at that today. I'll start by quickly reminding you what a monad is, how monad compositions work. And since most of my theory comes from the algebra side of monads, I'll also quickly remind you how algebra and monads are connected and what compositions of algebras are. I'll continue by giving you a sort of bird's eye view of how I prove my no-go theorems. Those are the theorems that prove when distributive laws do not work. And then I want to delve into the Bohm hierarchy. It's a data structure hierarchy, and it has given me a lot of inspiration and intuition about monad compositions. And that's the main thing I want to share with you today. And just because I'm known for putting proofs in my talks, I would like to end the last 5 minutes by proving one of my theorems to you. And it's called the too many constants theorems. So I hope you will enjoy. So very quickly, monads are categorical structures that are used throughout computer science. They're very useful for modeling data structures, such as lists and trees, but they're also good for modeling computational effects, especially in functional programming. Monads are really used for this. And there's lots of examples. And there's so many examples of monads really that Dan Marsden, my colleague and co-author, has made a slide where he lists all kind of weird things that turn out to be monads, like distributive laws themselves are monads. Who knew? It's kind of like category theory. Once you know what a category is, you start seeing them everywhere. It's the same with monads. Once you know what a monad is, you see them everywhere. Now, because they're so useful, we would like to compose them, because every single monad does just one thing. We have a list monad that models lists. We have a tree monad that models trees. But what if we want to model lists of trees? Then we would like to compose these two separate monads into one so we can model them simultaneously. And that is what you can achieve by using a distributive law. Now, before I can explain what a distributive law is, I need the actual definition of a monad. So here it is. A monad is a triple consisting of an endofunctor and two natural transformations. I'm mostly looking at the category set. So all monads I'm looking at are functors from set to set. And the natural transformations, eta is called a unit and mu is called a multiplication. And they satisfy the unit and associativity axioms, which may sound familiar if you're familiar with monoids. Now, we have loads of examples of monads. In this talk, I'm mainly going to focus on list, multiset, and power set. Multiset is also known as bag monad, and I will use the name bag because it's shorter and fits nicely on the slide. Now, if I want to compose monads, I'm composing their functor parts. That's really easy because category theory allows you to compose functors as long as their types are okay, which in this case, they're both functors from set to set. So composing them is really easy. And then the quest is to find a unit and multiplication so that the entire structure is again a monad. The unit is quite easy. You can just compose the two component units to form a new unit. That works beautifully well. The multiplication is a little bit more difficult, because what we want for the composite monad multiplication is to have a type from TS to TS. But if I look at the component multiplications and I just put them together like I did with the units, I get something from TTSS to TS, which just doesn't fit. So what I can do is just pre-compose with a natural transformation that fixes this type. If I switch these middle S's and T's here, then I can apply the multiplications, and then I get something I like. And this is exactly what a distributive law is. It is a natural transformation that fixes the type so that I can apply the component multiplications of the two monads. And now a distributive law needs to satisfy some axioms to ensure that the structure you get is indeed a monad. Those are not too important for now. The important message is, with a distributive law, we can compose monads, and that is really nice. However, they are very hard to find. When I started my thesis, very common monads, such as the list monads or the probability distribution monads, were not known to compose. It wasn't known if there was a distributive law for them, even though a composition of such monads would be really useful. The second problem is that the axioms of a distributive law are actually quite hard to check. They look simple enough, they're just some commuting diagrams, but when it comes down to actually checking them for specific monad compositions, you need to get into nitty-gritty details, and it's very easy to get lost, especially when you have several monads applied and then you're fiddling around, and it has gone wrong multiple times in the literature, which is quite painful. And the worst news of all, which is good news for me because it's my entire thesis, is that distributive laws might not exist. So looking for a distributive law is hard. So what I do in my thesis is I provide no-go theorems for distributive laws. And these are theorems that prove for a really broad spectrum of monads, if the monads share certain properties, then they cannot be composed. So don't even try to look for a distributive law. And I make these theorems using algebra. So let's have a quick reminder of what algebras are and how they work. Algebraic theory consists of a signature of operation symbols and a set of variables. And from these variables and operation symbols, you can build terms. And then you can reason about equivalence of terms using equational logic. And we also have some axioms that then define the theory. So good examples, well-known examples, are monoids and abelian groups. A monoid has a signature consisting of a constant and a binary operation, so taking two variables. And the equations that it holds are left and right units and associativity. I hope this is well known to everyone here. And then we have abelian groups, also well-known structure with a constant and a binary, but also a unary symbol in the signature. Again, the left and right units, associativity, now also commutativity, and an inverse equation. Now, these are two examples of algebraic theories, and the connection to monads is that the category of algebras form algebraic theory. You can form a free forgetful adjunction to the category set, and that will give you the monad. It's not a truly straightforward connection, but we do say that the algebraic theories present the monads. And you can learn a lot from the a lot of the monads by studying the algebraic theories that present them, which is exactly what I'm doing in my thesis. So now that we have an algebraic version of monads, I need an algebraic version of a distributive law to be able to prove something about distributive laws. And this is given by the notion of a composite theory. Instead of composing monads, I'm now composing algebraic theories. And the actual definition of a composite theory is quite complicated, quite involved, quite technical. But I want to explain it using the example of rings. Because rings are a composite theory of abelian groups after monoids. And notice this word after here. That's because there's a direction going on. And I'll point out to that direction slightly later on. So you build a composite theory by taking the signatures of both of the theories and taking the disjoint union of them. So here we have all of the operations from before, the two constants, the two binaries, and the unary operation. They form the signature of rings. And then the equations are the equations of abelian groups, the equations of monoids, and these two. These are interaction equations between the two binaries. In this case, they are the well-known distributivity of times over plus. And this is actually where the term distributive law comes from. It's from this, because this is the classic example of a distributive law. And the direction I mentioned earlier is because these interaction laws, as I really like to call them, they allow all the terms in rings to be written in a certain order. It's abelian group term, here the plus, with monoid terms inside of it. And these rules allow you to rewrite every term into this form. First, you have an abelian group term, and then you have monoids inside of those. And that will be important later on. That is what a composite theory is, basically. It's the idea of it. Now, my strategy of proving that such a composite theory does not exist is by starting to assume that it does exist. And I choose two specific theories to compose, like monoids and abelian groups, except that I know they do compose, and slightly different ones. And then, because I know that there is this interaction law, I don't know what it is. It could be different from the times over plus interaction law. So I can't assume anything about the interaction, but I do know that there is one. So I do know that I can write every term in a certain form. So I'm going to play around with that, manipulate them. And this is the technical part of all my proofs. And then eventually, I'm deriving a contradiction of the form x equals y, two variables equal to each other. And that, of course, means that it's an inconsistent theorem, and that's not what we want. So we don't have a composite theory that we want. So composite theories are impossible if you can derive this contradiction. Now, of course, this only gives me that two very specific theories do not compose with each other. But if I then go back to my proof and I list all the equations that I've used, all the axioms that I've used in my proof, then I can just list those as properties that make the proof work. For example, if my specific theory was abelian groups, but in my whole proof I've never used the inverse, then apparently I don't need that specific property of abelian groups, and I can just list all the properties that I do need, and then I get a general no-go theorem that holds for any theory sharing these properties. So now, instead of going more into detail about these proofs, let's have a look at their consequences. And I really like to use the Bohm hierarchy for this. It is a hierarchy of data structures that starts with trees, then lists, bags, and sets. And when I first learned of this hierarchy, I thought the name was obvious because, well, I'm Dutch, and in Dutch, boom means tree, so I thought it was just called the tree hierarchy. Until someone in England pronounced it Bohm hierarchy, and it was only then that I noticed that Bohm was capitalized. And in fact, it is named after Hendrik Bohm, a Dutch-Canadian computer scientist whom I'm honored to have in the audience today. He noticed a very pretty structure in these data structures, which I will show you now. And it's actually the structure that I'm going to use. If we look at the algebraic side, then the trees are presented by an algebraic theory with a constant and a binary operation. And the constant acts as a unit, both left and right, for the binary. And I've put the unital equations in brackets because you can also consider non-empty trees. And that means you ignore the constant in the signature. So you only have the binary operations and no equations at all. And those structures are called magmas, I believe. Then if I add associativity to this theory, then I get monoids. And monoids present a list monad. Then if I add commutativity to monoids, I get commutative monoids, which represent the Bags monads, multiset monad. And if I then further add idempotence, I get joint semi-lattices, which present a power set monad, or the data structure sets. So in these, if you look at the algebraic side, these data structures form this beautiful hierarchy where you just add one axiom at a time to get to the next structure. And I've chosen to study this hierarchy because the monads you see here are very practical monads. In your first course in computer science, you learn about trees and lists and sets. They're such basic data structures. And the theories that present them are beautifully simple. They have a signature with just one or two operation symbols in them, depending on whether you consider the constant or not. And associativity must be one of the most common axioms you want in a theory. They're even in the axioms of category theory. But even though it looks all so simple and beautiful, there is a lot unknown about these structures. When I started my thesis, one of the first questions I worked on was whether the list monad distributes over itself. That wasn't known, even though a list is such a common structure. And on top of that, the axioms of associativity, commutativity, idempotence, and units, even though they're really common, they display a wide variety of properties. Associativity and commutativity are linear equations, which have proven to be very important in monad compositions. Idempotence and units are not. So that's also interesting. So you have both sides, both the nice linearity, but then also equations that are nonlinear, so you can study both. Different combinations of these properties can do very funky stuff to your structure. So even though they're simple properties, there's a lot going on when you combine them. And that's why I decided to look at this hierarchy. So let's have a look at some results then. So these are indications of the yeses here are when the column after row is a composite monad via distributive law, and the no's are when such a distributive law does not exist. These yeses here, they follow from a theorem from Manes and Mulry. And here we have the power set monad does not distribute over itself, a well-known result by Bartek Klin and Julian Salamanca. And then there's a couple of results from me and Dan in there. So we see about half of the structures compose and about half do not, roughly. So that doesn't tell us much yet. So let's look at the non-empty versions of these monads, where I ignore the unit equations and I throw out the constant from the signature. Well, then suddenly it looks a lot better. Here we still have all these beautiful monads that compose by Manas and Mori. This is also Manas and Mori's result from their 2008 paper. And you see these slightly lighter shaded. These are results I have produced in the past 2 months. And because they're not published yet, and I told you earlier, people make a lot of mistakes in this because it's really tricky. I do feel confident enough to include it in my talk today, but I shaded them a bit to warn you, these are unpublished results. But what we can see from these 2 tables next to each other, here is where we ignore the units, and here's where we include them. It seems that units are quite bad for compositions. But it's not a very big data set, so let's extend it slightly further. We've already seen that turning the unit axioms on and off gave quite a lot of information. So why don't we do that with all the different axioms rather than adding them one by one? We just consider all different combinations. Now, this gives us a lot of structures, and not all structures are currently in use or have a name. So I've used this sort of naming scheme where I just list the first letter of all the axioms that I include. So I have UAC, means that I include the unit axioms, associativity, commutativity, but not idempotence. That is the naming scheme I will use. And this happens to be my code name for bags. And they all have the same signature. And if I don't consider the units, I throw out the constant from the signature. I just have a binary. So let's have a look at that table. Now it's a very big table because it's 16 by 16. So I've cut it up in quarters. And the first quarter I want to show you is where both of the monads have units. So we saw that that was a bad property. And indeed, this is the table. You see here all of my structures start with a U, so they all have the unit equation in them. And then I just systematically go through all the possible combinations of the other axioms. And we see that if you want to compose monads, having a unit in them is not a good idea. It's, yeah, a lot of them don't work. So let's have a look at where both of the monads do not have a unit. Previously, that looked a lot brighter. And that is this table. You see, none of them have a U in them, so none of them have a unit. And then I systematically go through all the combinations. And now we suddenly see that in the rows where there is idempotence, these rows here, a lot of monad compositions don't work via distributive law. Again, the lightly shaded areas are from results that I've produced in the past 2 months. All the other ones are published. So from this I conclude that idempotence is also a dangerous property for monad compositions, but not always, because here we have power set, non-empty power set monad, which does combine with non-empty multiset. So it's not always a problem, but usually. And then the other two, where one monad has a unit and the other does not, it doesn't add too much information. So this is the entire table. Here is the non-empty version. Here is where both have units. And these are the two missing quarters. Those don't really add any new intuitions, just that in every row where there's an idempotence, there's a lot of monad compositions that don't work via distributive law. So I guess that is my main takeaway from this overview, is that idempotence and units are bad equations to have in your theories if you want to compose monads, but not always. Sometimes they work. Now let's have a look at what these equations are and see if we can figure out why they are bad. Well, they look quite similar. They have a variable on one side, on the right-hand side, and then on the left-hand side, they have this little more complicated equation. And we see this pattern in some other equations as well. Here there's an absorption equation, also has a variable on the right and a slightly more complicated term on the left. And this, I think, is a crucial property in the failure of distributive laws. Because in my thesis, every single theorem I have that proves that is a no-go theorem for distributive laws has this property. It needs such an equation at some point in the proof. And I even dare to make this a conjecture. I would say that equations that reduce a term to a variable are necessary for distributive laws to fail, but not sufficient. And I know this is a bold statement, especially considering how new this whole area of disproving distributive laws is. So I'd be very happy to be proven wrong as long as that inspires someone to look at this. I think it's a very exciting field that we will see a lot more of in the next few years. So regarding the Bohm hierarchy, this would mean that I expect these little squares here that I've shaded in, they have neither units nor idempotents. I'm expecting those to have a distributive law. So challenge for the community, find one. Or prove that it doesn't exist, in which case my conjecture will fail, which will be very exciting as well. And with that, I would like to go to the next part, which is my too many constants theorem. This is by far my favorite theorem. It fell out a bit of an accident. At first glance, it doesn't look too important, but it has done a lot for me, and I will show you just how impactful this little theorem can be. But before I tell you what the theorem is, I need a little proposition, which I won't prove, but you can find it in my thesis and in the papers with Dan. And the proposition is about the interaction law. And I'm going to show you when things behave kind of like a multiplicative zero. I'll show you. So I'm going to ask one algebraic theory to have a term that can be reduced to a variable via substitution. There it is, the critical property I needed. And what I mean with via substitution is, for instance, if I have x times y with times here being idempotent, then I can replace this y with an x. I can do a substitution, and then suddenly it reduces to a variable. Same with the absorption equation. This term here cannot be reduced to a variable, but if I substitute an x into either y or z, then suddenly it is. So I need a term that does that, so that after I do a substitution, suddenly I can reduce it to a variable. Then on the other side, I need a slightly more technical property that's not too important. I do need a constant, which otherwise I'm never going to get to the too many constants theorem. And the slightly technical property is that for any term, if after a variable for variable substitution, it is provably equal to the constant, then it was already provably equal to the constant before the variable for variable substitution. It's a small technical detail, don't worry about it too much. But if I have two theories satisfying these two properties, then I know that in any composite theory, I must have the following interaction. So that if I substitute the constant of one theory into the term of the other, then it is equal to just the constant. And I call this a multiplicative zero because it's like 0 times x. The 0 is the constant from the abelian groups, and the times is the binary from the monoids. But if I do 0 times x, then that is just equal to 0 in rings. So that is the interaction I'm looking for. Substitute a constant of one theory into a term of the other, and then it reduces to just the constant. That's the interaction I need. So now we are ready for the too many constants theorem. I require that same key property again, but now I also want that term that can be reduced to a variable after substitution to have at least two free variables. And on the other theory side, I want at least two constants. Too many in this case is two or more. And both of these constants need to satisfy this slightly technical property. If we have these simple conditions, then there exists no composite theory of T after S. And that means if you look at the monad side, then there's no distributive laws for the monads presented by these theories. And I'm going to prove this to you. So let's have a go. Well, suppose that there is a composite theory. That's how I start all my proofs. Then we're going to apply the proposition that we've just seen to this term. This term S is the term that we asked for just here. It has two or more free variables, and I've named the two that I know it has. And after a substitution, it can be reduced to a variable. That's all I know about it. But then I know that the proposition holds. So I'm going to substitute both of the constants of T into this term. And by the proposition, I know that on one side it's equal to 0. That's this multiplicative 0 thing. But since 1 has the same property, it also is equal to 1. So I've now proven that in this supposedly composite theory, I have 0 equals to 1, but these are two distinct constants of my theory T. And that leads to a contradiction. The exact reason why that immediately leads to a contradiction has to do with some technical properties of composite theories. I think we can all agree that if I can prove that 0 is equal to 1, something must be wrong. And therefore, you cannot be a composite theory of T after S. So if you have these simple properties and two or more constants, then there's no composite theory. So let's have a look at the effects. Well, one effect that I haven't incorporated in this slideshow, but that I do say in my papers, is that it immediately pointed out a mistake in the literature. So it's very helpful to, as a sort of sanity check, if you find a distributive law, because these properties are so simple, it's quite easy to check if your distributive law has a mistake in it or not. But here I've taken the Bohm hierarchy again from the beginning with the units in, and I'm now interested in this area where they do form compositions. And I want to see if I can form iterated compositions with them. So I've listed them here. I've just used the first letters of the monads. So this is bags after trees, bags after list. That's this one here, bags after trees. This one here, bags after lists, bags after bags, sets after trees, sets after lists, and sets after bags. So those are the ones listed here. Now I want to know, is there a distributive law of these guys over these guys, or these guys over these guys? And well, you may remember from the ring example that if you have a composite theory, then it takes a disjoint union of the two signatures. So all of these, because all of these monads here have a unit, and so one constant in them, all of these will have two constants in them. And because the Bohm hierarchy has really nicely behaved monads, they all satisfy my theorem. And so none of those have a distributive law according to my too many constants theorem. it just immediately rules out any composition in that part of the table. So that's quite powerful for such a cute little theorem. And then we have this part of the table that is still unknown, but one of my other theorems in my thesis uses again this zero multiplicity axiom, the fact that we have this interaction of 0 times x is 0 if we satisfy some nice properties. It uses this on this side, and that one is able to rule out all of those. So if you have units in the monads, then if you're part of the Bohm hierarchy, iterated compositions are not going to work. Again, confirming that units are just not a very good property to have around if you are doing monad compositions. So in conclusion, I've shown you that not all monads compose by a distributive law. I hope that is clear by now. And I've shown you how I've used the Bohm hierarchy to both display my results, make them more visible rather than just dry theorems, but also provide intuition of how monad compositions behave in general. And this intuition has led me to formulate a conjecture that reducing a term to a variable, perhaps via a substitution, is really a key property for all of my no-go theorems, and might even be a key property for any possible no-go theorems. Who knows? And lastly, I've shown you that having too many constants in your theory combined with the multiplicative zero property prevents iterated distributive laws within the Bohm hierarchy. And with that, I am done. You can find my thesis on my personal webpage. There's also links to my papers there. Papers are all co-authored by Dan Marsden. He's amazing. And if you want to reach me and talk to me about this, please use my personal email address that is on this slide. So I'll have my PhD viva soon, and I'll lose my Oxford email address soon after. So yeah, thank you for your attention.
Okay, so thank you very much, Maaike. So I suppose we'll open the floor for questions. So as I said earlier, please use the raise hand feature if you have a question. I already see one question. So Paul, can you unmute yourself and ask the question?
Okay, it's a quite complicated question. So if anybody's got simpler questions that are related to what Maaike said, then maybe they should ask them first and come back to me.
Okay. So do we have other questions? So Paul, looks like you can go ahead.
Let me provoke some discussion then. There's some very interesting insights there that I've never seen things of that kind before. So congratulations on that work. So I'm thinking, on the other hand, of the classic cases where we have distributivity. So that is to say, let's say commutative rings and distributive lattices. So those are very fundamental things in mathematics, because well, firstly, the intermediate structure, that is to say let's say abelian groups and semilattices, right, are important for themselves as being linear algebra and linear logic. And then when you go to the composite theory, that's interesting because you take the dual category, that's an algebra, and you take the dual category and you get some notion of space. So you could turn the whole thing up again and replace the sets you started with spaces, and then build the algebra, topological algebra, and then you get sort of coming back again, you get a topological thing similar to the abelian groups or to the semilattices, and then you can come back, build the algebra up again. Now, it's a bit vague what I've said, because I've never really made this, all of this picture work fully. That's a reason why distributive laws are a good thing. And in those cases, you do have, well, idempotency is optional, but you do have both units. So that's, shall we say, rather than the question, invitation for further discussion and further research.
Yeah, definitely. There are cases in which both of the monads have units and things still work out. There were all those green fields. It's very interesting to explore the boundaries of that. What are the precise conditions of when the composition works and when does it fail? And yeah, I'm really excited to learn more about that.
So what are the situations where you are allowed to have two units and you get a distributive law?
Only ones that are in Manus and Morris. They all fall under Manus and Morris conditions. It's if you have linear equations on one side and units. Yeah, units are linear as well. Yeah. Commutative monad on the other side, and that is commutative monad in the monad sense, not in the algebra sense.
Right. So can you pin down, how much like a commutative ring this theory has to be?
Sorry, say that again.
Well, the canonical example is commutative rings. Can you pin down sort of how general the situation with distributive law in both units can be?
Yeah, so there is the paper of Manus and Mori has that pinned down quite nicely, and there's also work by Louis Parlan, who has done extensive research in this field. I don't know off the top of my head just how general that is, but it requires one of the monads to be a commutative monad always.
Yeah. Your central conjecture, if you take the contrapositive of it, it's saying if the theory has no equations between a term and a variable, then it had the distributive law. I'm afraid I find that very difficult to believe.
Yeah, I mean,
sounds like a very, very strong conjecture.
Yes.
I want more evidence of that.
You gotta be bold to get somewhere, right?
Well, I mean, yes, be bold, but I wonder how you're going to get the distributive law out of that condition.
Oh yeah, it's definitely not a constructive one at all.
No. Right. Okay. Thank you. I'll let somebody else have a talk.
Okay. Thanks. So there was one more question. Yeah. Please go ahead. You can unmute yourself and go ahead. Yeah.
Hey. So you've mostly worked in the category of sets, and lots of these monads do generalize to other categories. Say, for example, your list monad becomes the free monoid in a category, and your bags monad becomes the free symmetric one, like on vector spaces. So I'm just wondering if you've looked at no-go theorems in other categories in sets that may not have all the nice properties that sets does.
Not yet. I'm hoping to do a postdoc on this. My PhD has only focused on the set versions, and yeah, I'm hoping to start a postdoc to look into the categories beyond set and see what it does.
Cool, thanks.
Okay, so the next question is from Henrik Boom. Please, yeah, please go ahead.
Yes, hello. I'm kind of surprised that the hierarchy I thought of so long ago turns out to have this much rich structure. I never dreamed that it would be something like this. I thought it was sort of a trivial comment about some well-known data structures. But I find myself looking at these charts and wondering, first of all, is my intuition right that when you compose, say, bags over after lists, that what you get is a data structure that is a bag of lists? Or is it something entirely more complicated than that?
Oh, no, it's just that.
It's just that. I
There's some interaction.
have trouble figuring out how bags over bags could possibly compose nicely. Sort of like you invert the structures.
It's exactly just, yeah, bags of lists, and but then for that to be a monad structure, there needs to be some nice interaction, and that is what fails in some cases.
Yeah. Well, I was looking at one of the things that seems to work all the time, which is bags of bags.
Yeah.
And I'm trying to figure out how you invert the two bags in terms of a data structure. It's hard to imagine.
It's like the times over plus. So you.
Yes, it would have to be, wouldn't it?
Yeah. It's like the times over plus. So you distribute all the bag elements over the other bags and do a sort of inversion thing there.
I'll have to look at that in some detail to figure it out. Thank you.
Okay, so the next question is Tobias. Go ahead.
Hello. Thanks for the talk. I have a bit of a question that might be tangential, but do you know, so you talked about these monads composing into a new monad. What I'm wondering about is the other way around. Do we know anything about when a monad can or cannot be the result of a composition between two other monads?
Oh, I like that. I haven't considered that.
All right, so I guess your answer is no, but yeah, I'm thinking about this from another. It's related to something I've been looking at. Yeah, I don't know if you find anything about that, give me a shout.
I'll take that on board. Thanks.
All right.
All right. So Paul, you can continue.
Okay, so this is a simpler question. In the lattice cases where you've got idempotents, qualitatively the infinitary case is pretty similar. Can you generalize your results from finitary to infinitary theories?
I don't think so. I'm not sure. But I did see that Julian Salamanca has published a new result about the infinite case of lattices. That is on my reading list currently. I was going to look at that tomorrow. But I don't think my results generalize trivially to the infinite case.
Okay, thank you.
Okay, so do we have more questions? Okay, so if not, probably I would request all of you to unmute yourself and let's thank Maaike for a good talk. So thank you very much, Maaike. So to everybody, if you wish, you can stay for the post-seminar coffee break. Otherwise, you can leave now.